Welcome to Spring LIB.
Okay, we have two similar reactions. In each case, we have the same substrate. But we'll get different results in each time. And the first time we're reacting with H3O+. And remember that H3O+ is going to add OH in Markovnikov fashion. But that rearrangements are possible. What do I mean by that? Well, if you think about the mechanism, recall that for addition across a double bond, right, this double bond swings open. One side gets the H, the other side gets a carbocation, and it's going to be the secondary side that gets the carbocation and the primary side that gets the H. But what happens is that when we form this carbocation, we have a secondary carbocation next to a quaternary center, and that is the recipe for methyl shifts or rearrangement, which brings us instead to this intermediate, and that's where water adds. Oops, put the carbocation in the wrong spot. This intermediate, and water adds to the central carbon instead. And after a deprotonation step, we'll get that our product is like this. Okay, so that's the answer to the first question. The second question, though, is a different type of reaction. It's oxymercuration. Demercuration. Okay. It's a two-step reaction. And just like H3O+ before it, it adds an OH group. And it does so in Markovnikov fashion. Right, but it does not allow for rearrangements. No rearrangements. The reason for that is that there's never a carbocation intermediate. It's not part of the mechanism. You don't form a carbocation intermediate, and without a carbocation intermediate, you don't end up with rearrangements. So instead, we say, well, it's going to install an OH on one side of this double bond and an H on the other. And the OH, if it's following Markovnikov rule, will go to the more substituted side. So I'll redraw the substrate without the double bond. I'll put the OH on one side and the H on the other. Right, see how that's different than the water product, in which a whole methyl shift moved and the OH added to a completely different carbon.